One important type of calculus problem for the AP calculus test is the 1D particle movement questions, all right? So a lot of times these are calculator required problems. They don't necessarily have to be, but it's helpful to have a calculator for them. And that's often the way they're designed. So a couple of important things real quickly that we need to remember when we're talking about 1D movement. So we're going to have some position function. It might be x of t or s of t. And if we take the derivative of, so if x of t is the position, that is, maybe it's position on the x-axis, or we could be y-axis as well, if we do like y of t or something like that. Or sometimes s of t just for position. So, and then if we take the derivative of position, we get velocity. And then if we take the derivative of velocity, we get acceleration. All right. So we've got this kind of hierarchy here that position, we take the position and we take the derivative d dt, we're going to get velocity. And if we take the derivative of that, we're going to get acceleration. And what's the opposite of the derivative? Well, the opposite of the derivative would be the integral. So if we integrate acceleration, we get velocity. If we integrate velocity, we get a position or a displacement actually, right? So, all right. So those are important connections there. Well, let's check this out here. We've got a particle moving along the x-axis with the velocity given to us here as this function. And we've got a time constraint here. Okay, so we want to find a particle. Well, we know, first of all, that the position is at -5 when time is 0. Okay, so we need acceleration of the particle at time t equals 3. So first thing we've got to remember is that the derivative of velocity is acceleration. And I'd recommend that you write this down right away. The moment you realize that you're talking acceleration and you know velocity, write this down. That very likely might be worth some points. So we need to find that derivative. So v prime of t, if we go back up to our function here. Now again, this is a calculator question, so you could use the calculator there. And you don't even necessarily need to write it out when it's a calculator-based problem there. But we'll go ahead and write it out here just for good practice. So we've got the derivative using the quotient rule and the chain rule here. We're going to get something like this. Derivative of the top is going to give us 0.8 t, that's derivative of the inside, times the derivative of the outside, which is going to be 10, and when we multiply by 10, I'm going to erase that decimal point there. So 0.8 times the 10, and derivative sign is cosine. 0.4 t squared times the bottom, t squared minus t plus 3, okay, minus, because this is our quotient rule, top times the derivative of the bottom, and all over the bottom squared. So this thing is a mess. So you can see right away, this is not really the route we want to take. So, and the AP people are not going to necessarily be looking for that. What they want to see is they want to see that you realize that you need to find the derivative of this. And so this leads us to, at time 3, we need the acceleration is just the derivative of v at 3. And so you can do that. We can just go compute that. We don't even need to write that whole thing out. Use your TI Inspire. So skip all that stuff and go straight to TI Inspire, or if you have TI 89, okay? And you can do this on the TI 84 as well. There's a derivative key there, okay? We can enter the function in Desmos even here, okay, is what I've got handy on this that I can display. And so if I type in V of t, Desmos and a lot of calculators, they won't figure out the algebra of it. They won't give you the equation of V prime, but we don't need that. All we need to know is what is V prime of 3, and that's going to be negative 2.118. Remember, we want 3 decimal places, always rounded to 3 decimal places. So this is negative 2. And there we have it. So that's our acceleration there. Now, do be aware if there's any units here, and in this problem it looks like there are no units. It doesn't say this moving in feet or anything, it's just position, and time doesn't even have any units, okay? So not looking for units here. Find the position of the particle at time t equals 3. Well, position is an integral, and so we know that the integral from time 0 to 3 of v of t dt is going to be x of 3, because that's going up one level, sorry, not x cubed, but x of 3 minus x of 0, right? And that's just using the fundamental theorem of calculus. So writing that out, that actually probably is a point there. We're looking for this. We don't know x of 3. We do know x of 0. This is negative 5. All right, so this is x of 3 minus or plus 5, minus negative 5 there. Now, we need to find this, which we're going to let our calculator do, and then we're going to subtract 5 from that. So where we have x of 3, which is what we're looking for, equals the integral from 0 to 3 of v of t. Again, don't take time to write down that whole function. We're not the AP people aren't going to be looking for that. So let's go back to our calculator. I'm going to go back again to Desmos because that's what I can show here. You can use your TI Inspire or other calculator. Now on Desmos, you can actually do this. An integral is just start typing int. I believe it's under functions also. Let's check that out there. So under functions, there it is down there. Okay, so we're doing our integral from 0 to 3 of it, and we're just going to type. We're not going to type the function out because I've already typed it in up top. Okay, so you got to have it typed in like I did, v of t, and then we're going to need dt. Okay, and there it is right there. And while I'm at it, I'll type in minus 5, right? And there we go. Okay, so we had from 0 to 3 vt dt, and we subtracted 5. There it is right there. So we have negative 1.760, negative 1.760. All right, 1.760. Again, we don't have units. A lot of times in these problems we'll have units. This might be feet, inches, depends on what the units are given. Okay, great. Now we're going to evaluate this integral here and evaluate it with the absolute value, okay, and interpret the meaning. So again, this is just looking for understanding. Do you understand what it means? And so they're not looking for you to crank it out because it's a calculator problem. And so we're going to go to our calculator, and we're just going to let the calculator do the work. So we're going to come back up to here, and let's just take this here. So I'm just changing my function there, took off the 5 and change it to 3.5. We get 2.843. Actually, 844. Watch your rounding, okay? 2.844, okay? So 2.844. And now let's go ahead and do the integral from 0 to 3.5 of the absolute value of v of t. So let's go back to the function there and throw an absolute value there. And so we want to be familiar with where that is on different calculators. On Desmos here, let's see. We can use these floor things, but you can also just type ABS, should work. ABS, and then in parentheses, or I might put in brackets there. I'm going to close that bracket there. Okay. So, actually, we don't want ABS. It's just right here. Absolute value function. There we go. All right, so we get 3.737. All right, 3.737. We got to interpret that. 3.737. All right, and so then it says interpret the meaning of each integral in the context of the problem. All right, so this is the displacement. Okay, so the blue one here is the displacement of the whole particle is 2.844. So that's displacement for these 3.5. It doesn't say seconds, so we can't really say seconds, but t is between 0 and 3.5 is 2.844. Now this is the total distance. All right, so the absolute value takes all that negative, makes it positive. So we can say the total distance is 3.737. So they're looking for an understanding of that wording there, right? Displacement just from beginning to the end, and the total distance is 3.73. Okay. So last but not least, we got a second particle moving on the x-axis by this function here. And the question is, what time are the two particles moving the same velocity? All right, so we need their velocities to be equal. And so we're going to need to find the velocity. We'll call this v2 of t, which is equal to the derivative of x2 of t. So we want to remember this right here, this little picture. The derivative of position gives us velocity, derivative of velocity gives us acceleration, and then we integrate it to go backwards. All right, so, and that's fairly easy to compute. That's 2t minus 1. All right, and so we want to know when that is equal to v of t. So now if you have a CAS calculator, you just punch that in your calculator and solve it would be the thing to do. On a more basic calculator that doesn't have an algebra solve function, we can type 2t minus 1. Okay, so when you're using Desmos, if you do t, it won't like it. If you just do 2t minus 1, it doesn't understand. But if you do it as a function, it does understand. And so we want to understand where they're the same. Well, it's right there, all right? And so it will solve it. It's right there. And it's 1.571 is the x value. 1.571. Okay, so at 1.571 t equals that, v1 of t equals v2 of t. All right, now this question will show up also in other ways. Sometimes it'll show up, it'll say, when are they moving in the same direction? Well, they're moving in the same direction when they have the same sign, positive or negative. And if it's just asking the same direction, you got to do the same idea, find the velocity, but you'll need number lines. In this case, we want the exact same velocity. All right, so there you have it. That's a good example of a particle problem there, a one-dimensional particle problem. And again, these are your relationships here to remember there. All right, keep working hard. You're going to do great on that AP test, and be ready for these. These show up often.